So the other problems we were able to get by without solving a full 3x3. But this problem and the last problem, we pretty much need to solve a full 3x3. And I have a 150-pound crate hanging here. I have a cable AB, a cable AC, and a cable AD. My TAB vector is equal to TAB magnitude. The line vector, which is positive, as I go from A to B, positive 2 in the X, negative 2 in the Y, and positive 5 in the Z. And you get this unit vector. T from A to D, we go negative 2 in the X, minus 1 in the Y, and positive 5 in the Z. And I get this unit vector. As I go from A to C, I go positive 1 in the X, I go positive 4 in the Y, and positive 5 in the Z, and I get this unit vector. And my weight vector is 0, 0, minus 150. The sum of the X components gives me the X equation, set that equal to 0. The sum of the Y components gives me the Y equation, set that equal to 0. The sum of the Z components includes this minus 150, set that equal to 0. And this gives me my coefficient matrix. This gives me my right-hand matrix, which is 0, 0, positive 150. I can plug that into my calculator. And I get TAB is 52.4, TAD is 71.4, and TAC is 50.7. Solving a full 3x3. You should be able to do that on your calculator. It should be relatively straightforward for you to do it. And if it's not, keep working it until you can do it smoothly. And finally, there's actually one more problem, but it's really the same kind of problem. It's a full 3x3, except this time I've got 3 struts, and I have a force that's acting down on it. And so you kind of expect that all of these struts are going to be in compression. It turns out they're not, and I'll explain it to you when we get there. But I gave you a full force at the top, 20I minus 40J minus 25K. And the free body diagram is at A, because this is where all of the forces intersect. And I'm going to write these 3 unit vectors. So FAB vector is equal to FAB, magnitude. And the line vector from B to A is minus 3 in the X, 1 in the Y, and positive 8 in the Z. And you get the unit vector. Use the unit V function. FAC is you write the line vector from C to A. It's minus 2 in the X, minus 4 in the Y, and positive 8 in the Z, from which you get this unit vector. FAD, as we go from D to A, we're going to go positive 3 in the X, minus 3 in the Y, and positive 8 in the Z, from which we get this unit vector. And finally, my FA vector is 20, minus 40, and minus 25. If I write my equilibrium equation, some forces in the X is this guy, plus this guy, plus this guy, plus this guy is equal to 0. The Y is this guy, plus this guy, plus this guy, plus this guy is equal to 0. And the Z is this guy, plus this guy, plus this guy, plus this guy is equal to 0. So again, writing these things out neatly helps you get to these equations, which gets us to this matrix, a 3x3. And we can plug these coefficients into my sine-mult function. The right-hand side becomes negative 20, positive 40, and positive 25. If we solve this, we get FAB as positive 91.4, but FAC is negative 63, and FAD is negative 5.66. And you go like, what's going on here? So I assume these compression, I figured that these guys were pushing up on A, which is compression. But it turns out that AC becomes negative, which really means he's pulling. This guy's really in tension. And FAD turns around, and he should be going the opposite way, and it turns out he's in tension as well. And you go like, what? Why is that? How does that happen? And this is actually a good example of why you draw a free body diagram and then you write your equations based on that. But if an answer comes up negative, it basically means that the way you assumed on your free body, it just flips. And we'll do that a lot in statics. I mean, I try to spend time to intuit the correct directions on unknowns, but sometimes you're not sure. So let's talk about AD, for example. So AD is really in tension. If you draw a line from B to C, and rotate, take a moment about that BC axis, the horizontal components of this FA actually tip this little triangle here, this part of this tripod. The horizontal components of FA tip it this way about this BC axis. And so that's actually what causes FAD to turn around, to be in tension. The same is true with AC. So if you take a line from B to D, the horizontal components of FA cause this triangle formed of BAD to tip the other way, which requires this AC to flip and to go into tension. And so that's actually why they go into tension. And it's just a result of the particular components. I just grabbed these components just out of thin air, just thinking of a downward directed force at A. But these components are large enough in the horizontal direction to cause that tipping event to happen, which makes these guys turn around. FAB is positive, which basically means if you sum moments about this axis, then this force is pushing this triangle this way. And so FAB has to push to keep this guy in equilibrium. So it's an interesting problem. The results are interesting. I mean, the results actually surprised me, but it illustrates some valuable things from a statics perspective. So these are 3D problems, starting with really easy problems that work great on a test, to some pretty hard problems that you need to know how to work, that are appropriate in your homework, but they're certainly not going to happen every day. So, but you should be able to do all of this stuff. And certainly using your calculator and learning to use your calculator well, learning how to write forces along cables or along struts, getting the unit vectors is a huge part of that. But again, the calculator makes it super easy, which is another reason why I've urged you to get a TI-89 or a TI Inspire or a similar calculator that's capable of doing all this stuff.